The other thing that's very important that you understand is you understand what microscopic is and what macroscopic is. These things are the gas. So we can talk about a gas in terms of pressure, in terms of volume, and in terms of temperature. These are all things that I can measure in the lab, so I say they're macroscopic, or they exist in the world the size of me. Gases are actually made up of tiny particles, elements, sometimes molecules, and what happens is they're just bouncing into container walls. That's what's happening to the gas in the microscopic view. So on the one hand you've got like tiny little particles which have a mass and a velocity, and on the other hand those are exerting a pressure, they have a temperature, and they have a volume. You need to be able to reconcile these two world views. So essentially what you need to be able to do is you have to answer these two questions. What is temperature? Essentially what temperature is a measure of the average kinetic energy of a gas. So if a gas it gets hotter, what is happening? Well, the kinetic energy is increasing. And as you know, the kinetic energy is equal to half the mass of the particle times the velocity of the particle squared. If that's increasing and the mass is staying the same, well then you know the velocity of the gas particles must increase. So very roughly, the temperature of a gas is directly related to how fast it's moving. Now, the next thing you have to understand is, how do you reconcile the microscopic view of gas particles bouncing into walls? How do you reconcile that with exerting a pressure? Well, you know that pressure happens when a force acts over an area. At any instant, in this three-dimensional box that I have on the board, what is happening is there's gas particles in there, and millions of them, millions and millions, are bouncing off this wall here. That wall has got some area. If that is L and that is L, the area of that side we all know would be L squared. Now I can figure out what the force is. I just figure out what the force of one gas particle is, and I multiply it by the number which are striking it in any given time. So now I've got a force of the gas particles divided by the area. That's why they exert a pressure. Why is it that heating up a gas increases the pressure? Well, you've got two reasons really. You can say the gas particles are moving faster, and therefore they hit the walls harder, so the force increases. That's fine. You can also say gas particles are moving faster, so they hit the wall more frequently, so there's a greater force on any given area, and that's fine as well. So now you've reconciled pressure from the macroscopic to the microscopic. The last thing is, why does a gas take up a particular volume? If I take the example of a balloon, the balloon's got loads of gas particles in here, and they all, when they bounce off the wall on the inside of the balloon, they exert a force out in the wall. By Newton's third law, the balloon surface exerts a force back on the gas particle in this direction here. So that's why the particles never get out of the balloon. Of course, what happens is, on the outside of the balloon, there's loads of gas particles as well. And when they bounce onto this surface of the balloon, what happens is they exert a force in. Now, if I say, for instance, I come along and I blow into the balloon, what happens? Well, I'll put more gas particles in there. So now what happens is there's a greater force out than there is in. And so what happens? Well, the balloon grows. But now what happens is all of these particles are in a greater volume. And so by these particles occupying a greater volume, the pressure in here goes down. And now the pressure inside the balloon is equal to the pressure outside the balloon. Thank you very much.